All right, I'm gonna go over how I would personally solve this big combination circuit problem. And I apologize if my voice sounds a little rough right now because I am feeling kind of rough right now. Anyway, uh, you can see I have the circuit drawn out. I also have the table kind of filled out with all the known information. But the first thing that we need to do is we need to try to simplify this combination circuit as much as possible. This is something that I suggest you do if you're having trouble figuring out which resistors you should put together. You should try to color in the wires here. So I'm choosing blue for the positive side of the battery, and I color the wires until I hit a resistor. Choose red for the negative side of the battery, color in the wires until I hit a resistor. And then I choose just different colors for the different wires that exist between the other resistors. And so remember, these colors represent voltage differences. All right. One of the most difficult things uh, about combination circuits is to really figure out where you need to start and what resistors are okay to combine and what resistors are not okay to combine yet. So taking a look at this, uh, I have this resistor. The 80 ohm resistor goes from blue to orange. This one goes from orange to red. This one goes from orange to green. This one goes from green to red. This one is green to purple, purple to red. And so nothing is immediately uh, jumping out and saying that they're parallel. Uh, but to me, it looks like these are in series. And that may be just it may be easy for me to see just because I'm more experienced. If that's a little bit difficult for you to see, like why those are in series and why you should tackle those first, I would suggest instead of trying to find that, you can see how this resistor is green to red, and this set of resistors also goes from green to red. And so we have a parallel set here, but we need to combine the 15 and the 20 ohm resistor. They are definitely in series because there is only one path through those resistors. And so what I'm going to do is I'm going to combine those first. I always suggest redrawing circuits. So I'm going to redraw this. And those two resistors combine into one. And so the circuit is going to look essentially like this. I'm going to write the resistances. I'm going to forget the units to save time. But these two resistors combined into one, and because they're in series, the equivalent resistance is just 35 because you just add them together, right? 20 plus 15 gives you 35. Another helpful thing that you may want to do is keep the coloring scheme from the previous circuit. And so if I do that, then the circuit is going to look something like this. What color did I use? I used green. Okay. Now, clearly, these two are in parallel. They both go from green to red. They both have the same voltage across them, so they are in parallel. We can add them together using the parallel resistance formula. And so when I combine those together, our new circuit is going to look something like this. This is still 80. This is 30. This is 50. And a 35 ohm resistor plus a 70 ohm resistor. We get 23.33 Ohms for that one. All right. Again, I'm going to keep the coloring from the previous problem. Okay. Now what do we do? Hmm. Well, we have blue to orange, we have orange to red, we have orange to green, and we have green to red. So nothing is in parallel right now, but again, this one and these two together are definitely in parallel because they both go from orange to red. So I'm going to combine these two resistors. We are almost done. Those two resistors are in series because you have to go through both of them in order to complete a loop. And so you add them together, that's 73.33. All right. Lastly, what we have available are these. Oh, let me actually color in the wires again, just to make things. Okay. And so again, we can see these are definitely in parallel. They both go from orange to red. And so our final, well, maybe not our final combination of resistors. This one is still 80 and 1 over 30 plus 1 over 73.33, 1 over that number, and I get 21.3 approximately for that one. And so we have a series circuit here. If I wanted to, I could redraw this into a one resistor circuit. Doesn't help too much because I already know what the total resistance is going to be. And so this helps us find our total resistance. This is going to be 80 plus 21.3. That's 101.3 ohms. Okay. From here, uh, if you know two out of the three between V, I, and R, you can just use Ohm's law. Remember, Ohm's law is V equals IR. And so to find the total current, I take 200 divided by 101.3, and I get 1 point, let's go to two decimal places, 1.97. Okay. Now that we have our totals, we can start working backwards. This, I'm going to look at the final circuit that I made. I know that the total current going through this is a 1.97 amps. This is a series circuit, so both the 80 ohm resistor and the 21.3 ohm resistor get 101, or sorry, they both get 1.97 amps. However, the 21.3 ohm resistor is a combination of resistors, so that's not really helpful to us, but the 80 ohm resistor is its own thing. And so I know that the 80 ohm resistor also gets 1.97 amps. Anytime you find two out of the three between V, I, and R, I suggest finding the third thing because I promise it will be helpful. So to find V, we just take I, 1.97, times R, which is 80, and I'm getting 157.6 volts for that one. Okay. What that means is that we have 200 total volts for the battery. That's the total voltage of this system. This 80 ohm resistor just took a 157.6 volt step down. That means this step down has to be 200 minus 157.6. So this is 42.4 volts. What you also could have done to find that number is you could have taken the current 1.97 and you could have multiplied it by the 21.3 and you should get something at least really close to 42.4. Any discrepancies is just due to rounding. I'm going to use the 42.4 volts. And how this is relevant is that this voltage step, again, if I color in the wires, this is what it looks like. I just found that blue to orange is 157.6 and the orange to red is 42.4. Now I'm going to start working backwards. I'm going to go back to this circuit that I drew. Orange to red, I just found was 42.4 volts. The 30 ohm resistor is its own thing. So 42.4 volts for the 30 ohm resistor. All right, once again, let's find the third thing, 42.4 divided by 30. I'm getting like 1.41 amps. Okay. What that means is that the current, and let me use a different color here. Let's use green for the current. That means the current going through this branch is 1.41 amps. We know the total current coming from the battery. So the total current coming from the battery was 1.97. That 9 does not look like a 9.97. Okay. Well, remember, in a parallel circuit, the current just splits up. So if I have a total of 1.97 and I have 1.41 going through that branch, the current going through that branch must be 1.97 minus 1.41 or 0.56. Okay, so I have 0.56 amps going through the 73.33 ohm resistor. But again, the 73.3 ohm resistor doesn't actually exist. That is a combination of taking another step back. That is a combination of the 50 and the 23 ohm resistor. So I know that there is 0.56 amps going through that branch. The 50 ohm resistor is a thing. And so I'm going to write in for the 50 ohm resistor, we have 0.56 amps. 0.56 times 50 for V equals IR gives me 28 volts. That means orange to green is 28 volts. My work at the end is going to look really messy, but hopefully you're following along from the beginning. All right. If orange, so a couple ways you could do this. I know blue to orange is 157.6. And then uh, I know orange to green is 28. I could do 200 minus 157.6 minus 28 to get the green to red transition. Or you could do, you know that the orange to red transition is 42.4 and orange to green is 28. Well, 42.4, the 42.4 that we have here, minus 28 gives us 14.4. So that means this voltage transition, green to red, is 14.4 volts. Okay. So green to red is 14.4 volts. The 23.3 resistor doesn't actually exist, so I'm going to take another step back. Oh, the 35 ohm resistor is also not a real thing, but the 70 ohm resistor is. So the 70 ohm resistor must get 14.4 volts. 14.4 divided by 70 gives me 0.206 amps. Okay, home stretch. I know, let's use green again. I know the current going through here is 0.56 amps. I just found the current going through there was 0.206, which means that the current going through that branch, 0.56 splits up into 0.206 and something else. So 0.56 minus 0.206, I'm getting 0.3354 amps. Okay. The 35 ohm resistor isn't a real thing, but the 20 and 15 are. And because they're in series, they both get 0.354 amps. Man, my computer is struggling with this. Okay. So 0.354 for both of these. All right. Then you just do V equals IR. 7.08 volts for that one. 5.31 volts for that one. All right. The hard part is done. So I'm going to use the P equals IV formula to find the power for all these. These are all watts, by the way. Okay. So now that I got all these values, this is a great way to check to see if you did things correctly. I got 394 for the total power by taking 200 times 1.97. But what I'm going to do is I'm going to add all the individuals that I got, and they should get pretty close to 394. And I'm getting 393.29. Sure, it's not exact, but if you consider how small a 0.71 difference is compared to 394, that is pretty close. I'm pretty confident that this is correct. Hopefully, this long video helped. And yeah, enjoy.